Hello, my name is Gregor Fonaszewski, and I'm talking to you today about REST and how we are using REST within our cloud computing efforts. This is done as part of Indiana University and the Department of Intelligent Systems Engineering. I'd like to acknowledge Jeffrey Fox and the TAs Bo, Hango, Miao, Tyler, and Vibartha. To understand where we are coming from, we need to be first revisiting what the web was originally about. And we had a very simple workflow. In the original web pages were represented and contained some content. Web page was formulated through some syntax annotations such as HTML. Then the web page was hosted on a server with a given URL. That's a Uniform Resource Locator. Clients typed in the URL from the web page in a browser. The web page was being fetched, and the data was being presented in the browser. The page is then rendered in the browser itself while interpreting the HTML messages. That naturally was a wonderful model for representing information. However, soon people wanted to have an enhanced workflow while accessing objects. And they wanted to access objects, to create them, to read them, to update them, and to delete them, and represent information within these objects. This is now where REST comes into play. REST stands for representational state transfer. And the important part is to note that REST is actually not a standard, but that it is an architectural style for designing networked applications. It is based on the concept of being stateless, interface between client and server, and contains cacheable communications through a protocol. Although REST is not based on HTTP, in most cases, an HTTP protocol is used to implement REST-like services. In contrast to what other people may actually tell you, REST is not a standard. The representation is part between the client and the server. We need to be naturally representing the information so that client and server can understand what happens. Another important feature is that we talk about resources versus actions. Some mechanisms focus on actions such as get me that information, get me that resource. But in the REST style, we are based on resources where we say, I have a resource such as a computer. Get me the description of the computer. And in order to facilitate this, REST is developed around 6 constraints. Before we go to these constraints, let's just take a look at the interaction that we actually have. One of the interactions is that we communicate through an HTTP request from our clients to web servers, and the web server returns an HTTP response back to the clients. Remember, REST is not bound to the HTTP protocol, but in our case, when we are working with web servers, this is the most natural form of communication. Let's take a look at what a REST resource means. REST works on resources, and we are using this concept of a resource as a source for information. Example resources are, for example, documents, images, resources with temporal information included, such as weather or your load on your computer. And we often have to really deal not only with a single resource, but with a collection of resources. So it's important to understand that although we talk about resource, we are often interested in resources. So the resource is a conceptual mapping to a set of entities. A resource can be a singleton, that's a single instantiation, or a collection, with multiple instantiation. Customers is, for example, a collection of resources, and customer is a single resource, so it's singleton. So this is just one example. Computers is a collection of a single computer, of many computers. Resources can contain sub-collections of resources so that we can build group and hierarchical mechanisms. And here the same thing. So we are talking here about single account versus multiple accounts where customers are included in the account. So an account is then a single resource, but the sub-collections contain accounts, and a user or customer could have multiple accounts. REST is resource-based. We already pointed that out before. And that makes it possible for us to define API around REST services that are easy to understand. The API from other frameworks are often based on verbs, and the API that we are talking about here is based on the resource. We can have multiple URIs pointing to the same resource, and we can have multiple levels in the resource itself addressing potential sub-collections. Here, when we take, for example, a look at one of the URIs, we have on our local host a web server on the port 8080. We are having a resource that we call My Service. In that resource, we have another resource that is called Users, which is a collection. In that collection of users, we have one specific user. Let's call that particular user Jane. The representation between client and server needs to be well formed and follow a particular pattern so that we can interpret the data that is being sent to us. We typically are talking about the state of the resource that is being communicated to us through these representations. The reason for that is we are issuing a call to our web service. At that time, that particular resource may be of a particular state. However, we have to remind ourselves we are talking about a stateless service interaction, so that we don't actually have that information right available. It's going to be gathered through some queries to us, and that result is being forwarded back to us. This allows us to formulate a very simple RESTful API. And typical examples of representations are JSON format, which is simply this bracket notation where we have attributes, values as comma-separated values, or an XML representation where the XML is being used as a tag and identifier for that particular field, and the values are between the tags of that particular attribute. The representations is largely similar, and out of convenience we probably will be using JSON format instead of XML format because it's easier readable to the human. REST is an architectural style, as we have already pointed out. We have requests that are being sent, in our case, through HTTP. That means we can post data that helps us to create and updating it. We can read data to make queries, and we can delete data while we, for example, remove content. The architectural style that is being represented through this is called CRUD. We have operations such as create a resource, read the content of a resource, update the content of a resource, delete the resource. As part of the HTTP protocol, we have convenient messages such as get, put, post, and delete that have been introduced into the HTTP protocol to support such operations. These methods can naturally be used to implement a REST service. We have already spoken about the URIs. We have, through the URI, a uniform resource identifier so that we can identify a particular object on which, or object collection on which we execute the CRUD operations. And the status and the representation of that object are returned to us in the HTTP response body that we are obtaining once we are querying one of the URIs. The architectural constraints that we have within the REST services is that we have a uniform interface, it's stateless, it's cacheable, we have a client-server interaction, we have a layered system, and we could have code on demand being executed as part of our architecture. Let's just take a look a little bit more on the constrained uniform interfaces. We already have seen that we define a client-server interface, and we have 4 guiding principles here. We have pointed out it must be resource-based. Manipulation is being done through the representations of the objects. So this means if I want to change something, I need to be using the representation of the object to execute that change. And the messages in themselves are self-descriptive. The constraints are stateless. The server, which is the host for RESTful service, does not contain the client state. That means I maintain as my client my own state, and I have to synchronize through whatever mechanism I need with the state of, for example, the server to update my objects. The messages are, again, self-descriptive, helping the stateless methodology because it contains enough information for the server to process it or for the client to update its state. We have a uniform interface between client and server. So the servers do not need to worry about a fanciful user interface because that is being part of the client interface. And we don't actually have to worry about the state, which makes this overall system a little bit more scalable. In addition, the REST service can be cacheable. That means the server's responses are cacheable explicitly, implicitly, and through negotiated mechanisms. We have a RESTful layered architecture system where the architecture is being implemented in multiple layers to separate concerns and to allow for modularity of that implementation. Here it's important to know that we are looking at, for example, the client, which doesn't know who it is connected to, for example. That's one of the examples. We have a URI sent to it, but we don't need to know exactly the details of that particular web service to which we are connected to, because we are communicating just via URI. Software and hardware intermediates may exist between the client and server to create a forwarding of messages between client and server. That allows us to have multiple hops between client and server so that the information can be flowing between them seamlessly. This improves the implementation of extreme scalable systems that need to be dealing with tens of thousands or millions of connections. We also have the ability to introduce code on demand. That is, a RESTful server can temporarily extend a client by transferring logic to the client to work on, for example, the information that they have received. That's, however, the only constraint that can be broken within the REST service to stay REST services. So That means we have to fulfill all these constraints that we have in order to stay fully compliant to our REST service architecture. Staying in compliance with this architecture allows us to maintain simplicity, scalability, portability, adaptability, and also reliability. There's a number of frameworks available within REST architectures in a variety of languages. Spring, Express, and Rails are some examples, but for this current activity that we are looking for, we are looking into Eve, which is a Python-based framework, which is built on the microservice framework Flask, which provides very good flexibility, but also offers great convenience of being simple to use. To mention other efforts, we have to look into, for example, industry. Industry is using REST services frequently, such as, for example, the Google Cloud API uses REST interfaces. And you can find more information out about the Google Cloud platform and how they are using REST services from the given URL. Naturally, Amazon RESTful web services exist, in which you use the RESTful web services to communicate with backend services that are hosted at Amazon. And there's a variety of services and APIs offered in Amazon that actually support this. And the API here to notice this is the Amazon API Gateway that can be used to create RESTful web services. It's not only providing you with an API, but also allows you to have a fully managed service hosted within Amazon to create, maintain, monitor, and secure APIs that scale while you are developing them through the REST paradigm. In addition, Amazon API Gateway not only exposes REST, but exposes Lambda functions, which are small functions that are being executed on their framework, which we will be going into later on in our class. Other examples in industry include Microsoft Azure, where we have also RESTful web services that can be formulated. And it contains a platform for hosting cloud applications and services in an efficient manner as far as advertisement from Microsoft is concerned. Similarly to Amazon Web Services, Azure also provides an architecture and a workflow to host RESTful web services seamlessly into their cloud offerings. Azure supports, as any other REST framework, libraries including Python and Java, but naturally we have things that are supported, such as ASP.NET. So let us return to where we want to develop some REST services ourselves, and we provide you with a short introduction to what is called REST Eve, which has the advantage that is A, provided in Python, and B, has been used by many thousands of people that are actually developing REST services. So we know that the system actually does work, and we can utilize this very easily. What we need in order to do this, we naturally need a database in which we can host the objects. We need a configuration file that allows us to configure the REST service, as well as a launch script that allows us to launch the REST service so that we can connect to it. So let's take a closer look at this, what we need. We assume that you have Eve installed as a package on your computer. And that's really easy because you can do this with pip install, and you can do this either in Python 2.7 or Python 3.6. And the only thing that we really need to do is to create a run program that we put in our directory. And we need to be importing from Eve the package Eve. And in order for us to show you something a little bit more interesting, we thought, well, let's figure out the processor name that we actually have on your platform and or on your computer that you're running. So therefore we're importing also from platform, which is a Python package that allows us to query that information. So first we need to be creating an application, Eve, and the information to Eve, the configuration is passed in this particular way through a file called settings.py that's hosted in the same directory. Now, one thing that we need to be doing now is we need to create a URI or a route to what will happen when I'm asking my web service for a particular resource. In this case, we create a resource that we call processor. We define a function called processor in which we call the platform processor and redirect the output to name and then return the name itself. The addup.route operation that you can see this is called actually a decorator in Python, which allows us to make sure that the function called processor is associated with an appropriate URI that we have for this particular service. Now, the only thing that we now need to do in the main program of the Python function, of the Python program, is to simply call the application and call the run method because it runs forever. And in order for us to start this, we just simply type in python run.py. And to obtain the result, we can just simply issue a curl call, because this is what we are doing with curl. We just issue a request from the command line to the server with the given URI that we are passing along. And here we are passing along the localhost processor to identify what comes back. So please try this out, and you will be able to obtain information about your processor. One of the things that we need to be considering is in our previous example, this was a very small example which didn't have any database associated with this. But in many cases, we have thousands and thousands of data points that we would like to query. And it is sometimes convenient to just have a real database associated behind the Eve framework that we are just exposed to you. And the way Eve works, it has actually built-in mechanism to query, for example, MongoDB. MongoDB is a document-based database which addresses scalability and flexibility in a nice fashion, but also integrates very nicely with Eve due to its REST closeness. It stores data in JSON objects. That's naturally ideal for us, because if we return data as a JSON string and the data is already included in the database as a JSON object, we can simply return the JSON object. We just need to be making sure that we are asking for the right object. So it makes it an ideal choice for doing RESTful web services. MongoDB is a NoSQL database, so we don't have to worry about SQL database tables. And don't typically use table joins or store procedures that you're used from traditional databases that are based on SQL paradigms. The querying of MongoDB, therefore, is relatively fast because I don't have to do any data translation, because the object is just given back to me. We are using within MongoDB the CRUD operations so that it maps easily out into the REST framework. So because of this, we can actually map any operation easily from the CRUD operations from the REST server to the CRUD operations of the MongoDB server. MongoDB is often also offered in cloud services, and we have to talk about what advantages do we have for having it hosted in a cloud versus having it hosted ourselves. One example for a cloud-based services is MLab, which are offering a database as a service for MongoDB in their hosting services. Development naturally can be done in all the languages that we expect because it's a client-server interface, so there's nothing really so special about it, but it's noteworthy that all these language interfaces do exist and have an easy access to this. Naturally, that can also be done with a self-hosted service. So there is no differentiation between the hosted service and the self-hosted service. The advantages of hosting such a database in the cloud is that you don't have to manage it. The disadvantages, however, are somewhat significant, and we have to think about this. First of all, we may actually have to pay for the service, depending on what service agreement we need to have in order to keep that system stable, up and running. The second of all is MongoDB itself is really easily to deploy. If you have privacy concerns for data that is being hosted in the database, we need to be first figuring out if the service level agreement that we can have with MLab or another service provider addresses these privacy concerns. At the same time, all connections must be secured between the externally hosted framework and service and our client. However, sometimes we actually execute our connections on the same server where our local database is being hosted. There may actually not be a need for client security in that particular case if the connection comes from the local host. Thus, it could be an effective way for smaller installations that run behind a firewall and to make these connections less secure. Naturally, in a larger enterprise, you want to secure every connection. So for our class, we don't actually require you to host the data in a cloud service. And in fact, we don't actually want that because we believe that some of the data that we will work with is private, and you may want to not do these kind of things on a hosted service. There are many alternatives to MongoDB that you could also be integrating into Eve. That includes text-based databases and other SQL-based databases, but also potentially other systems such as CouchDB, Cassandra, OrientDB, and Azure DocumentDB. And these databases should not be confused with non-SQL databases that support, for example, key-value storage models such as DynamoDB, Redis, because they are targeting different other domains. One of the things that I was recently exposed to was this particular table, which showcases in some sense how popular certain databases are, and a particular company has identified some kind of evaluation criterion. We don't want to go into if this is a good or bad evaluation criterion. They have just defined one. We just take a look at what it actually means if we were to believe that this is a good criteria. As we see from here, Oracle is evaluated to be mostly mentioned, and MySQL and SQL, so the first 4 entries in this table are all related to SQL databases. Then we have MongoDB, and somewhat later we have some other databases that are document-based. So let's reduce the table to focus on the document-based databases. And if we do that here in this particular slide, we see that MongoDB is about 10 times more popular than any of its competitors that we have while focusing on document-based NoSQL databases. As you can see here in this table, we have 330 versus 37, which is Amazon DynamoDB. And we see there's a significant difference between the popularity of these databases. When we take a look at the trend of the databases and how popular they were, we see that MongoDB naturally had a head start and is very popular. And we have to remind ourselves the ordinate is specified in log scale. It's not a linear scale. So as you can see, this is significant because this means 300 and this may actually mean just 30 here. So don't confuse this particular table, and MongoDB really stands out here, while the other ones are very similar to each other, where Amazon and CouchDB are the more popular ones, and or Couchbase are the more popular ones, with some others losing a slight popularity. However, we see also other more recent efforts coming in here that you can explore while looking a little bit more closely at this table. But for us, that's also one of the reasons why we have chosen MongoDB as the backend database, due to its popularity within the community. Previously, we have just talked to you about how do we start up Eve, and we need to be configuring Eve through a settings activity so that we know that the backend system is being set up through MongoDB, on which machine it's being hosted, which port, and what's the database name that we have associated with the MongoDB. And Eve makes that really simple for us because it allows us to specify a configuration file either directly in the directory, then we don't have to specify the settings equals settings activity because it will be automatically read in if it's in the same directory as the run.py program, or we are specifying it simply as an JSON object that we are passing along to the instantiation of the Eve application. So when we then run Eve up run, it will use these settings that we have here while starting up your application in Eve. An important other point is that there is this domain variable, and this is the variable that tells us which resources we are storing in our Eve service. And that can be formulated through a schema, and the schema is based on Kerberos standard that you may want to look up, and provides you with a mechanism of defining objects in a nice consistent fashion with error checks. In order for us now to run this activity or this Eve service, we are distinguishing two different modes. One is the system mode, in which we are running Eve as a super user, and you can integrate these startup of the Eve service even in launch scripts, so that when you reboot the particular machine, the script will be rerun automatically. And this is naturally part of a production-like system. On the other hand, we have a user mode in which we are just simply running Eve by hand without sudo. And in our case, we actually want to do that because we want to be making sure that we can modify and customize our services, restart it, and make sure also that we shut it down so that no security exploits could happen after you're done with our activities. So as you now have seen, this is relatively easy to develop a REST service with Eve. And we would like you to develop REST services based on our NIST Big Data Reference Architecture you may want to take a look at the volume 8 of NIST NIST Big Data Reference Architecture and identify an object that you may want to start out working. Initially, I recommend that you go out and look simply at your computer system and report maybe some information that is dynamically obtained by calling a Python function to the calling entity from a client side and expose that particular information through your REST calls via the URI. With this, I would like to thank you for listening to us, and I hope that you will be able to now dive deeper into REST. I recommend you to read up on REST on the internet, and in our handbook that gives more pointers for you to get started and start developing an Eve REST service. Thank you.